Fusion Mobile, quality e-learning experience on the go.
Good morning. Welcome to Fusion Mobile e-learning clinic. My name is Sonia Olaoluwa and I'll be taking you through physics. Our first topic in physics talks about units and measurements. And in this topic, we'll be considering the following items. That's fundamental units and quantities, submultiples and multiples of units, derived quantities and units, dimensions of physical quantities, measurements generally, then we'll concentrate on measurements of lengths, time, mass and weight, volumes, and finally we'll consider the degree of accuracy. So, let's start. Fundamental quantities. Just like the name sounds, fundamental. When you say something is fundamental, it talks about the rudiments, the aborigines, the beginning points, the place where every other thing comes out. So fundamental quantities sounds they are the baseline, they are the basic quantities that we always work out through our study of physics. These quantities will keep popping up over and over again. We'll use them either directly or inside other quantities. Now these quantities are few in number, there are just 7 of them. We have them listed as time, length, and mass. These are the most common 3, which pops up in almost every physics question you see. And we also have other fundamental quantities such as intensity of light, such as electric current. We also have amount of a substance. So, what are the units of these quantities? We have very many different units you can use to represent distance, but we have a standard international standard unit which is accepted everywhere in the world. That is meters. Of course, distance can also be measured in inches, can be measured in centimeters, can be measured in kilometers, depending on the gradation. But internationally accepted units for distance is meters, while that's for mass is kilograms, that of time is seconds, that of intensity of light is candela, that of current is amperes, and mole of a substance or amount of a substance goes with mole. In the next few seconds, a question will pop on your screen. We just want to see how much of what we've spoken about that you understand. Welcome back. So, I believe what we've spoken about so far, we talked about fundamental units, we listed 6 of them. We have mass, represented by m. Its unit is in kilograms, that's kg. We have time, represented as t. We have units and quantities. SI unit is seconds. We have distance or lengths, represented by S, and its unit is in meters. We have electric current, represented by I, its unit is in amperes. So let me use the official A. So I have amount of a substance, which goes by with the unit mole. Most people do represent it with mole being spelled in full. And intensity of light, measured in candela. So, I haven't spoken about fundamental quantities and units. Let's consider submultiples and multiples of units. Submultiples and multiples simply are English words used to describe gradations. Multiples talk about things in growing size, while the word sub actually means below. So it talks about things in reducing sizes. So when we talk about multiples, it talks about meters. Now, when you have so much of meters, we want to measure very plenty meters. We need a particular unit that can carry much more meters, and that's where we come up with the idea of having multiples of units. And peradventure, you want to measure weight, and you have a particular thing that has so small weight and you need to be measuring it in the lower part, or even distance in the lower part, the distance between this point and this point. It cannot be measured in kilometers, cannot be measured in meters. So we need a gradation system which is lower than that of the standard, which is the reason why we come up with submultiples and multiples. So in submultiples and multiples, usually have powers, negative powers, and all of them come in powers of 10. All of them are multiples of 10. So the submultiples have negative powers, while the multiples have positive powers. We have submultiples as 10 raised to the power minus 1, which goes with the word deci, just like you have in decimeter, decigram, and the likes. And we have its counterpart, which is the one of 10 raised to the power of plus 1 rather, which goes by the name deca. Just like we hear in decagon. Well, it's just an adoption of it. And also we have the centi, which is 10 raised to the power of minus 2, and we have also have the centi and the hectare. Also, we can proceed to check up the milli, and mega. And we jump to raised power of 6, that's minus 6, and plus 6. Minus 6 goes by micro, and our plus 6 goes by hexa. Of course, some people use hexa. In some cases, we see giga come into play. So we can have hexa or a giga. Giga is not so common in physics being used. We use more of hexa in physics. And also, when we come to power of minus 9, we have nano. Power of minus 12, we have pico. I haven't spoken about fundamental quantities and units. Sometimes we have difficulties in measuring these units because we have so much of a particular unit, a particular quantity we want to measure, or so little of it that the official standard units cannot represent it properly. Such a case as we have, we want to measure the distance between Lagos and Ibadan, and you want to measure it in meters. You'll be having several thousand meters. So why not go for a simpler word as kilometers? Kilo there is a multiple that is being used in physics to express a very large increment. While also we also have units that also can be used to identify smaller components, and these ones are the ones that are called the submultiples. Peradventure, you want to measure the distance between this point and this point here. You also, of course, you cannot measure the entire distance between these 2 points in meters, because a meter is much more longer than that. So you have to look for a gradation which is smaller, where you can do your measurements more accurately. And these smaller gradations are described as submultiples. So we have multiples and submultiples, and these multiples are done based on the power in relation to 10. They are done based on they are multiples and submultiples of 10. That's what we do apply in our units. So let's take some of them. We have some of them listed out here. We have deci, which is a submultiple representing a thing reasonably big because it is the closest to meters, as it is raised to the power of minus 1. And we also have centi, which is divided by 100 actually, which is a power of minus 2. We have milli divided by 1000. which is a power of -3. We have micro divided by 1 million, which is a power of -6. And then we have nano, power of -9, and pico at power of -12. Also on the multiple side, we have deca, which is multiplied by 10, that's raised power of 1. We have hecto, which is multiplied by 100, which is 10 raised power of 2. We have kilo, of course, 1,000, a power of 3, 10 raised power of 3. Of course, we have micro, which is divided by 1 million, and of course, a power of raised power of -6. We have nano, which is power of -9, pico -12. When we come to the multiple side, we have deca, which is raised power multiplied by 10, that's raised power of 1. We have hecto, which is multiplied by 100, raised power of 2. We have kilo, which is raised power of 3, that is multiplied by 1,000, and mega raised power of 6, multiplied by 1 million. We have giga, raised power of 9, and tera, raised power of 12. Of course, you have to also always bear in mind the submultiples always have negative powers, while the multiples have positive powers. The submultiples are smaller quantities, while the multiples are larger quantities. So you might find it in application as megameter, megawatts, gigawatts, and such. You can have words like microfarad, nanofarad, picofarad, and we'll come across many of these things in our study of physics. Earlier we talked about fundamental quantities and units, and I told you that fundamental quantities and units are fundamental quantities. They are the basic quantities in which other quantities come out of. So which quantities come out of fundamental quantities? I was expecting someone to have asked me that all along. Well, that's what will come up with the issue of derived units. Just like the word says, derived. When you say something is derived, it means something was gotten from another thing. So derived units are derived quantities. They are quantities that can be measured based on whatever measurements that come up from 2 or more fundamental quantities. And on certain occasions, you can have just one fundamental quantity forming a derived quantity. A very unique case of frequency is such. But let's proceed and see what we can come out of. So, which kind of quantities are we talking about? Look around you. Think about anything, any quantity I have not spoken about today. Yes, that's it. You have your area, which is actually a combination of distance in 2 times. Your area is always measured as length multiplied by breadth, or length multiplied by height, or length multiplied by, or whatever formula it may be. It always comes up with the units meter squared. That shows us that meter has repeated itself twice. That is, distance has been covered on 2 different occasions and put in together to form one particular quantity. Like we have it in your area. Area is distance coming together on 2 different occasions, either as length and breadth, or half base times height, or whatever formula you can think of in which you can measure your area. It is distance put together in 2 different occasions. So that's why whenever you're writing the formula, the units rather, of your area, it always comes out as meter squared. Same thing you see in one of my most favorite units, and that's velocity. I love it so much because I like speed. Velocity actually is represented as meters per second. Let's make our M look good. Meters per second. So you see now in the case of velocity, it's not meter coming up a million times, but now you're comparing meters with seconds. You're comparing time and distance. So you put it together, you get a different quantity. You put up, there are so many of them. Resistance, angular displacement, very many of them. The number of derived quantities we have are so numerous we can't count them all. Every now and then we'll come up with new ones, because we keep discovering new things that make us need to develop new formulas and new expressions to describe them. So, derived quantities, the most common ones that we would work with more often: acceleration, which is represented as meters per second square. We have our weights. Yes, some of you may want to argue this, but your weight is actually a force. It is not the same thing as your mass. Your mass is the number of particles in a thing, while your weight is the force, is the effect of that number of particles, the effect rather of gravitational pull in a particular location on that number of particles. So your weight is actually measured in newtons. And we have many of them as that. Think about dimensional analysis of physical properties. What is this dimensional thing about? It's all simply trying to see how derived quantities are being developed. It is a principle that explains how different quantities, which originally were nothing to us, how they were being developed. And having a very good knowledge of this can always help you in your examination when you do not remember the formula. Yes, imagine you are asked to find a particular thing and you're given the units, and the unit is in something like kilogram per second. All you just need to do is look at whatever parameters you have and fix them together. How do these things merge to get you this kilograms per second? And that's what this dimensions of physical quantities rather talk about. So it's an extension of derived unit. It's us actually taking our time to analyze how these properties are developed. So the basic things to keep in mind are the fundamental quantities. What do we use to represent them? What are their representations? This is where you really need them. How do we get these derived quantities? That's what we want to start considering now. Okay, let's start from simpler ones. The ones that when we look at their units, we can easily predict what and what are coming together. We have quantities like velocity, oftentimes represented by with a v, a small v. A small v because we also have volume, which goes with a big V. Now, velocity. When we're considering velocity, velocity is the unit of velocity is meters per seconds. So, what entity produces meter? That is length. And what entity produces second? That is time. Of course, per. So, this is just a dimensional analysis of velocity. So, we can say V, that's velocity, equals L t raised to power minus 1. And to simplify it further, instead of having the minus 1, using our law of indices, raised to power minus 1 means 1 over t. So that will give us L multiplied by 1 over t, which give us L over t. How about taking one more example from something a bit more technical, as force. Well, we cannot really tell so much about force from the unit, which is the SI unit, because the SI unit of force is newtons. But we can tell about force because we know how we can calculate force. So let's go ahead and look at how to calculate force. Force is calculated as mass multiplied by acceleration. Now, hold that thought. Acceleration is still a bigger one, very big. So let's simplify acceleration further. Acceleration is calculated as velocity divided by time. Now, hold that thought again. And then we'll come to the last one. Velocity is calculated as what we got the last time. Length divided by time. So, we can take our velocity and take it into our acceleration. Taking our velocity into our acceleration, we'll have length divided by time multiplied by 1 over time. And simplifying this further, we'll have our acceleration to be equal to length divided by time squared. Now, taking this into our force, we'll have our force to be equal to mass times acceleration, which is L divided by T squared. And that will produce the answer ml over T squared. And that's how we solve questions having to do with dimensions of physical properties. We have many other ones that we can work on. You can try out power, work, and many more. Measurements. When we talk about measurements, simply has to do with us. I don't want to use the word measure to describe measurement, but that's actually what we do. We take a calculation or an estimation or quantifying of what we have. We quantify what we have. Peradventure, you want to measure a distance, you bring out your meter rule and you measure. You want to measure your weight, you bring out your weighing balance and you measure. You want to measure the mass of a substance, you use the mass balance and you measure. But what are the things that we need to take note of when we want to do our measurements? In doing our measurements, we must be conscious of how our measurements are being taken. It's not all kinds of scales or measuring tools that can be used to measure the particular kind of measurements we want to take. That's what I want us to keep at heart. But let's break it down one by one. Let's take the major fundamental properties and then we'll go into maybe some derived properties. Let's take those ones first. Length, for example. Measurement of length. Measuring our length, there are a lot of things that we can use to take measurements. Starting with your meter rule, which actually measures the entire 1 meter. Go to our measuring tape, which can be used to measure sometimes more than 1 meter. Talk about the builder's tape, which can actually be used to measure kilometers, up to 1 kilometer. In fact, some of them do measure more than kilometers. We have our classical ruler, which of course most of our rulers measure just up to 30 centimeters. Now, all these measuring tools can be used to measure different things, but not all of them can be used to take measurements of what we need to measure accurately. Peradventure, you want to take measurements of the diameter of this marker I'm holding. It would not make much of sense to use your conventional ruler or your tape rule because it will not give you an accurate measurement. But there are other tools that we can use to take this kind of measurements, and that brings us to the use of vernier calipers and micrometer screw gauge. Vernier calipers are measuring tools, and they are used in measuring diameters of volumes of quantity of things, diameters of circular objects, and sometimes they can also be used to measure depths. Of course, your conventional vernier caliper has a diagram, an appearance of what I am drawing on the board right now. It has an appearance something like this. Now, in this particular caliper, this caliper can take 3 kinds of measurements. It can measure external diameters. So I put my marker into my vernier caliper and I measure externally. It can take measurements of internal diameters, which is what the ones at the top take, and also this line at the bottom here is used for measuring depths. So this is a vernier caliper, and in our measurements, the gradation system. In your vernier caliper, you see a gradation system of something appearing like this. That's when you take a closer look. You take a zoom at what this region of it would look like, where the measurement is actually being taken from. You see something like this. It's continuous actually. Let's say this is 3, 4, and 5, and then it will have gradations 1, 2, 3, 4, 5, 6, 7, 8, 9, and same thing applies here. Don't mind my drawing skills, and the measurements go on. At the bottom side of it, we would have another gradation, which usually fall between 9 of your upper gradations, but it is graded in tens, and you have something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, to take our measurements on our vernier scale, the first thing you take notice which measurement is before your vernier reading. This upper part is known as our main reading, while this lower part, this one restricted to just 10, is known as our vernier reading. So the first reading you take is your main scale reading, and whatever answer you get there, you add it to your vernier scale reading. Your main scale reading, from this one, we have our main scale reading to be 3.1234. So our main scale reading equals 3.4. But on our vernier scale, how do we measure our vernier scale? You start observing on which of these lower ones does an upper scale, that is a main scale, fall on the same line with it. In this particular case, I have 1, 2, and 3. I have my 3 falling on the same line with a particular main scale. So that's called my vernier reading. Main reading and vernier reading is 2. To get your final reading, 3. So to get our complete reading, what we do, we multiply our vernier reading by 0.01 and we add it to our main reading. So the formula is final readings equals main reading plus 0.01 multiplied by vernier reading. When we do that, we would have 3.4 plus 0.01 multiplied by 3, which would give 3.4 plus 0.03, which equals 3.43. And of course, our vernier readings are always in centimeters. So that's how to use our vernier caliper, and basically the most difficult of all the measurements of lengths. But all our measurements, you use your tape rule. You can also take measurements. Yes, something to be very careful of. When you are taking measurements, always make sure you are looking at whatever measurements or whatever points you are measuring to directly. Make sure your eye is in line with that point where you are measuring up to. Because if you are measuring from above, there is a chance you might be measuring more than what is supposed to be. And if you're measuring from below, there's a chance you may be measuring less than what it is supposed to be. So measuring in a line of sight, that is the appropriate manner of measuring, especially in the laboratory. It is very important that when you want to take measurements, you take measurements along your line of sight. This is to avoid error due to parallax or parallax errors, as whichever one you're more comfortable with. They all mean the same thing. Parallax errors are errors caused by human mistakes. So line with your eye, that is, it should be in your line of sight. Your eye should not be up and you looking slant or downward at the measurement, or you be down and looking up or slant to it. You should always make sure that you are looking at it at a degree of 90. This would help you avoid parallax error in your practicals. And parallax errors actually do have a lot of effects on whatever results you may actually be trying to get in your practicals. Measurement of time. Our time is measured in seconds. Of course, many of us do know that reading we're taught when we're in primary school, or should I call it nursery rhyme now? 60 seconds, make 1 minute, 60 minutes, make 1 hour. Yeah, you may think it was useless, but my dear, it's very, very important, like right now. Because you have to work with it almost every time you're solving questions having to do with physics. Especially when the examiner wants to test your knowledge of these things. They might give you a particular question and tell you to calculate, convert what is 100 kilometers per hour, convert it to meter per second. You have to come up and calculate how many seconds will you have in 1 hour, how many meters will you have in 1 kilometer. So these are some of the places where we find these things popping up. And many of us, well, I know you enjoy it when you're working with it. So there are also many different tools we can use to calculate time. Of course, one of those such tools is your calendar. I know you may not believe it, but your calendar is also a tool for calculating time. Only that it calculates time in days, weeks, and years. And many of us do not really see it as very important. But also, apart from your calendars, we also have your wristwatch. Your wristwatch calculates time in minutes and hours accurately. But in the laboratory, we do more of using our stopwatch, which actually measures time in seconds, milliseconds, and other gradations as such. So, like I earlier said, when we're talking about submultiples, it depends on how much of time you are dealing with. Maybe you are dropping a pen, you want to calculate the amount of time to take this marker to drop from my hand to the floor. If you are not using the right measuring tool, if you are using your wristwatch to time it, well, I wish you well. But if you are using a stopwatch, you will get your accurate measurements. And you should decide to take measurements of how long it will take this marker to drop from this height to my hand. You cannot use your wristwatch to time it. You would need something so accurate as a stopwatch, which would actually measure in seconds, centiseconds, deciseconds, even if possible, milliseconds, to give you a more accurate timing. But if you try also to use a stopwatch to check how long it will take you to drive from Lagos to Ibadan, it doesn't really make sense, because you also have to keep recording and recording. But you can just simply use your wristwatch and measure how long, how many hours, because you're talking about hours now. So you have to use the appropriate tools to take such measurements. Same thing applies when it comes to measuring of mass. Mass, of course, you should use your different mass measuring tools. Sometimes you measure mass based on the mass of other objects. Most times, that's how mass is measured, based on mass of other objects. But also, if you want to measure the mass of an electron, it's not possible for you to get an electron you place on another scale and measure the mass. So you need to use something so sensitive to changes in mass as a countermeter. And also, if you also want to measure something like a mountain, you definitely don't want to use a countermeter. It would not give you any measurement. It will just show you error. So you choose the appropriate measuring tools. Same thing applies to weight. I earlier stated that weight is different from mass. Yes, weight is measured in Newton. So we have different measuring tools for measuring our weights. If you go to the place where they do sell iron, you see them. Some of them do have different kinds of measuring apparatus for measuring our weights. We have the normal weighing spring balance. Most of those spring balance does not measure more than 100 newtons. Now, if you're trying to use a spring balance that can only measure 100 newtons to measure something as heavy as 5 meganewtons, the scale would be exceeded and no measurements would be recorded. Similarly, if you're using a scale that can measure meganewtons to measure something of 3 newtons, your scale would not even move. So you have to choose the appropriate scales in these measurements based on how big what we want to measure is. Measurement of volumes. Volumes are oftentimes measured based on the shape and appearance of the entity you want to measure its volume. Peradventure, you want to measure the volume of a cuboid or a cube. A cube, of course, goes by V equals L cube. And cuboid is length times breadth times height. You have your cone, 1/3 your radius squared times the height. Also have your cylinder that goes with pi. Your cone rather goes with 1/3 pi height times r squared. Measurement of volumes. Now, volumes oftentimes are measured based on the shape or appearance of the objects that we want to measure. We want to take the measurements. For instance, you have a cube. Yes, you measure your cube using the formula cube equals L cube. That is your length. Since all the sides are equal, just multiply it by itself 3 times. And your cuboid goes with length times breadth times height. Your cylinder goes with pi r squared, which is r represents your radius and your h represents the height. While your cone also goes with 1/3 pi r squared h, which is also radius and height, respectively, r and h. So we also have other shapes, many of them. Your hexagons and other shapes like that, other objects like that. They have different forms, different shapes. Your sphere and the likes. They all have their individual formulas. And apart from these ones, we also have some objects that do not have a specific shape. They just have some irregular shape like that. So how do we take measurements of the volumes of such objects? What we do, we get say a conical flask or a particular, let me use the word bucket now, because I think that's what we all can relate with. You get a container, you fill it up with water, and you take the object, you drop it into it, ensuring that it sinks completely. Now, once it sinks, of course, since the bucket is filled with water, or the container rather is filled completely with water, the container will spill water out of it to accommodate the incoming object. So the water that comes out of the container would be taken, and measurements of how much volume that water occupies would also is the estimate of is actually the amount of volume the object that was immersed is taken. So that is how we take measurements of irregular shapes, the volumes of irregular shapes. So let's talk about degree of accuracy. In physics, we are always concerned about precision, accuracy. You must get it right. And that's the reason why we have always been talking about using the right apparatus, using the right measuring tools. You don't just choose any measuring tool and start measuring. Of course, you must choose the one that is suited, that would give you a measurement that is accurate. So let's talk about degree of accuracy. When we talk about degree of accuracy, we talk about the chances that are given to error. Yes, as accurate as we may believe we have been in our measurements, we also have to, our measurements can never be fully accurate unless we have taken into consideration how much chances of error can creep in. That is what degree of accuracy focuses on. So you see measurements, especially in the practical sections, they tell you a measurement or you want to buy a particular bolt or a nut, and you see them, they tell you it is having a diameter, it is M6 plus minus 0.1. This is a dimension M6 plus minus 0.1. The M6 is talking about the actual size of your bolt or your nut, and the 0.1 plus or minus is talking about how much of chance is given to it that it could be the error. Now, if I know many of us may actually not understand this particular M6 0.1, so I'll break it down something much easier for us to understand. Maybe we'll have something like you draw in an engineering drawing. You have something like a representation of 10 centimeters plus or minus 0.05. 10 centimeters plus or minus 0.05. It means an allowance of 0.05. Now that 0.05 will also share the same units as the expression in front of it. So it's a 0.05 allowance of error, probably measurements. Maybe you can get an oversize of 0.05. Maybe you cannot find that exact size. So it means that particular thing can accommodate up to something as small as 9.95 centimeters or up to 10.05 centimeters. So that is degree of accuracy. This particular expression at the back here shows us to what level is our measurement accurate. So it's possible that there is some error. Now, if sometimes some people do use plus alone, which shows that there is no negative measurement. You cannot reduce the measurement. You can only increase it by so degree. And some only use minus alone to show that you can only reduce it. You cannot increase it beyond that certain limit. And that's what degree of accuracy is about. So let's take it all up from the start. In this topic, we considered units and measurements, and we talked about fundamental quantities and units. We discussed fundamental quantities as those basic quantities from which all other quantities come out of. We also talked about multiples and submultiples of units, and we talked about them. We explained that multiples of units are talking about the increasing powers or increasing quantities of a particular entity, and submultiples are reducing quantities of that particular entity. We talked about derived quantities and derived units as those entities, those quantities that are derived, that are developed, that are adopted from the original ones, which are the fundamental quantities. Fundamental quantities, we listed them: time, distance, temperature, electric current, mass, luminous intensity, amount of a substance. We also discussed the dimension of physical properties, explaining that fundamental quantities merge together, combine together in different ways to develop derived quantities and units. We looked at measurements, and in measurement we talked about accuracy in measurements, how to measure, avoid parallax errors. We talked about measurement of lengths using vernier calipers, using tape rules, meter rules. We talked about measurement of time, can be done using your calendar, your wristwatch, your stopwatch. We also talked about measurement of mass and weights using counterbalance, using weighing balances, spring balance, and the rest of them. We talked about measurement of volumes. Volumes can be measured from the description of the object, that is the shape, appearance of the object, or if it is an irregular object, can be measured using immersion in water or a liquid, and we measure the amount of space, volume occupied by the displaced liquid. Also, talked about degree of accuracy to describe to what extent the measurements that we have taken is accurate, is perfect. So it gives us what allowance, what tolerances that that particular measurement has taken into consideration. And if there is any other thing that you don't understand in this particular topic, some part of it will be further explained when we look into the practical aspects of the topic. So, in a few seconds, some questions will be displayed on your screen. Try to handle them, and we'll see you in the next class.